Hello, Chem 2 class. I'm going over the Chapter 16 study guide, and I'm, of course, yeah. So for your upcoming test. All right. So if you're watching this right now, this is of course going to be on YouTube. So yeah, I'll try not to make too much of a butt out of myself. So with that being said, I think I'll go ahead and start going over the lesson. Okay, so chapter 16 study guide. So here we go. Let me make that smaller. Why don't I? Okay, because you don't really need to see me now, do you? Okay, all right. So that being the case, let's go ahead. All right, so let me put this on cursor. All right. Okay, so number one, which is not a characteristic property of acids? A, acids taste sour. That, of course, is a characteristic property of acids. B, it turns litmus paper from blue to red. Okay, so yeah, acids do that. So you wouldn't uh, put acids on red litmus paper because it would stay the same. But if you had, put an acid on blue litmus paper, it should turn it red. And likewise, if you put a base on red litmus paper, it's going to turn blue. But if you put a base on blue litmus paper, it's just going to stay the same. Okay. So number C, reacts with metals to yield carbon dioxide. That one's kind of iffy, right? Yeah, that one doesn't make sense. All right. So the answer, of course, is C. That is not a characteristic property of acids. D, of course, it neutralizes bases. Acids do that. And E, they react with carbonates to form to yield carbon dioxide. So the answer there, of course, is C. That's the only one that's not true. Number two, which is the formula for the hydronium ion? And of course, the hydronium ion is H3O plus. Now remember, we use that interchangeably with protons. So of course, if you have a proton in water, you're going to form a hydronium cation, right? So when we're talking about the pH of aqueous solutions, the P, of course, is the negative log of anything. So the negative log of H plus concentration is the pH, or the negative log of the hydronium ion concentration, because we use those two interchangeably. Moving on to number three, in the reaction, carbonic acid plus water yields hydrogen carbonate ion plus H3O plus. The Bronsted acids are, so of course, carbonic acid is an acid. Now acids, Bronsted Lowry acids, they donate protons, and Bronsted Lowry bases accept them. So the carbonic acid, of course, is donating a proton to water, and as a result, it's going to have one less hydrogen on it, and it's going to be one unit more negative. Okay, which it is on the opposite side of the equation. HCO3 minus has one less hydrogen. Okay, now the other acid, which is the conjugate acid of the base, in this case water, of course, after water accepts a proton, uh, because it's the base, you're going to end up with hydronium cation. So this is indeed an acid because it's the reaction, we're going the opposite direction from right to left, and of course you would the hydronium cation would of course be donating a proton to the bicarbonate anion. Okay. All right, so the answer there is going to be, let me see, what is the answer? It is going to be D, right? It's going to be hydronium cation plus H2CO3. All right. Number four, which one of these statements about strong acids is true? All strong acids have hydrogen atoms bonded to electronegative oxygen atoms. That's not true. Of course, you have strong acids that's not the case. Uh, for example, HCl, HBr, HI, they're all strong acids. Okay, strong acids are 100% ionized in water. This is true. Strong acids are 100% ionized in water. Uh, that's what makes them strong acids. Okay, that's the definition of a strong acid, 100% ionized in water. That being the case, if you know the concentration of the strong acid, then you also know the concentration of hydronium ions, or hydrogen cations. So then, of course, if you get the negative log of that concentration, you will have the pH. The conjugate base of a strong acid is itself a strong base. That is so not true. The stronger the acid, the weaker its conjugate base. So of course the answer is not C, uh, and we know it's not A. So of course the answer is B. But let's go ahead and look at D and E to see why that's not the answer either. D, strong acids are very concentrated acid. No. That's like saying 100% $100 bill. If you have $100 bill, you have a lot of money. It's a very strong currency, but you need a lot of $100 bills to have a lot of money. So you can have a large number of $100 bills. You can have a large number of pennies. Okay, the same way you can have a large concentration of strong acids and a large concentration of weak acids. So the answer is definitely not D. E. Strong acids produce solutions with a higher pH than weak acids. No. Remember, the stronger the acid, if you have similar concentrations, if you have the same concentration, the stronger the acid, the lower the pH. So the more acidic it is, the more acidic your solution is, the lower the pH is. Okay. All right. So moving on to number 5. Number 5. What is the concentration of protons in a 2.5 molar HCl solution? Okay. So I think I'll just go ahead and get my screen snipping tool, and I'm going to snip that, aren't I? Let's go ahead and snip this. I'm going to hit copy, and I think I'll go to my whiteboard. I'm going to paste this on my whiteboard. Okay, so I really didn't have to snip this. It was fairly obvious how to do this problem. Now, since HCl is a strong acid, and if you guys will remember what your strong acids, well, the strong acids that I gave you. This is not an exhaustive list, but HCl, HBr, HI, okay, then we have HNO3, I have H2SO4, and I have HClO4. Okay, so HCl, of course, is hydrochloric acid, HBr is hydrobromic acid, HI is hydroiodic acid, HNO3 is nitric acid, H2SO4 is sulfuric acid, and HClO4 is perchloric acid. So anytime you have those acids, the acid concentration and the H plus concentration are one and the same, and I have no idea why I just snipped this, because the answer, of course, is going to be 2.5 molar C. Okay, all right, but yeah, there's no sense in crying over spilled milk. All right, so let's see what we got here. Let me go back to my so let's say I'll do number 6 now. Number 6, the hydroxide ion concentration of a 1.0 times 10 to the negative 3 molar barium hydroxide solution is. Now remember, barium hydroxide is one of the few strong bases I might add, where the hydroxide concentration and the base concentration are not the same. That's because you have 2 hydroxide formula units. Two hydroxides per barium hydroxide formula unit. Okay, because of that factor of 2, all I have to do is multiply 1.0 times 10 to the negative 3 times 2, and I get 2.0 times 10 to the negative 3, which is the concentration of hydroxide. So the answer there is C2. Okay, so 5 and 6 is C. All right. Let me go down to my answer key to make sure that that's what I put. 5 is C and 6 is C. All right. Let's see. 1 was, let's see. 1 was C, 2 was C, 3 was D. So CCD, CCDB. So let's see what I have right here. CCDB. Okay. All right. So yes, so far so good. So number 7, what is the H plus concentration of a 4.8 times 10 to the negative 2 molar potassium hydroxide solution? Okay. Let's see what we got here. So now this one, I guess I do need to snip this bad boy. Copy. All right, copy that, and then I'll go to my whiteboard. Now, why don't I clear this bad boy? All right, then I'm gonna hit paste. All right, now what I'm gonna do this time, I'm gonna pull up the calculator on my computer. This just so you guys can see how I'm inputting the numbers. I should have done this before, Uh, let's see what I have right here. Let me see. That's actually the calendar. Let me do that again. Find the calculator. Calculator. There we go. Okay. All right. So pulling that right over here. Okay. Let me see. All right. So now we have my calculator. Now, guys, what the heck just happened? Oh, okay. All right. So now, of course, now we can do this one of two ways. I can use the fact that my H plus concentration times my OH minus concentration is equal to 1.0 times 10 to the negative 14, which is the autoionization constant for water. Okay. Uh, well, that's probably the best way to do this. So since we know, since we're trying to find the H plus concentration, I'm going to say my H plus concentration is equal to 1.0 times 10 to the negative 14 divided by my OH minus concentration. Okay, just a little algebra there. And then, of course, since we know what the H plus concentration is 1.0 times 10 to the negative 14, which is autoionization constant for water, divided by 4.8 times 10 to the negative 2. Okay. Oh yeah, potassium hydroxide is a strong base, and so my potassium hydroxide concentration and my OH minus concentration are one and the same. Okay. So yeah, I left that little part out. Okay, so let's see what we have right here. I'm going to say 1.0, and let me find times 10 to the, let me find negative 14 equals, okay, and it did not put it in scientific notation. All right, well maybe if I squinch it up, no, it's not going to put it in scientific notation. Okay, all right, well, yeah, I apologize for that. Divided by 4.8 times 10 to the negative 2 equals, oh yay, put that one in scientific notation. Now since this is good to two significant digits, that means my H plus concentration is okay. Every time I use my pen, my stylus, the calculator goes away. Okay, it's 2.08, so that's going to be 2.1 times 10 to the negative 13. So 2.1 times 10 to the negative 13. And let's see, that's going to be E, right? The answer there is going to be E. Yay. So let's go back and look at number 7. Answer for number 7 is E. So let me make sure that in my answer key it's also E. Okay. And number 8. Let's say, so number 8 says a 0.10 molar HF solution is 8.4% ionized. Calculate the H plus ion concentration. All right. I don't know. I think I just might, well, nah. Do I want to do this? Yeah, I'll snip it. I'll snip it. First, let me get rid of you. Then I'll go ahead and Okay. Now, if you guys recall that formula, what was it? Percent. Get my trusty calculator. So I'm going to say 1.0 times 10 to the negative 14 equals, okay. All right. Okay. All right. What happened to the 4? Wait. Oh yeah. Oh yeah. I know what happened to the 4. They exclude that. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14. So it's 1.0 times 10 to the negative 14. So I'm going to divide that into 1.6 equal parts. And yeah, they were nice enough to not put this in scientific notation. So let me count. See, this is why you should always have your calculator in scientific notation mode. Okay, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15. All right, so that's going to be 6.25 times 10 to the negative 15. Okay. All right. Yes, that's just wonderful. All right. Yeah, they have a few questions for me. Why? Of all the times, they could pop up. Why would it happen while I'm doing a recording? I mean, come on, guys. Okay. All right. I'm sorry about that. Okay. So of course we know that the pH is equal to the negative logarithm of my H plus concentration, right? All right, so I'm going to go ahead and get the, so my pH is going to equal to the negative logarithm of 6.25 times 10 to the negative 15. All right, so pH is equal to, let me go ahead and plug in my calculator. I'm going to hit C, I'm going to clear that, and I'm going to hit 6.25 times 10 to the, let's see, negative 15 equals, what did I just do? Okay, let me do that again. I'm gonna say 6.25 times 10 to the negative 15. Okay, and I'm gonna hit the logarithm of that, and I get a negative 14.20. And of course, if I hit the negative of that, I get a positive 14.20. Now, of course, since I took the logarithm of a number that has 3 significant digits, my mantissa is good to 3 significant digits. So my answer is, of course, going to be 14.204. Okay. All right. Yeah, now that's one of the nice ways of doing this. All right. At least I think it is. Oh, wait. No, I just reported this to too many significant digits, didn't it? So this answer was only good to, this number was only good to 2 significant digits. So at least I think it is. Yeah, so my answer is only good to 14.20. Okay. All right. And let me get my nice eraser tool right here. Okay. Now, the alternative way is, what they did is they took the negative log across this entire equation, and they were able to come up with this pH plus POH is equal to 14. All right. So remember, the P is the negative log of anything. All right. The negative log of anything. So of course, if I get the negative log of my OH minus concentration, I can find my POH, and of course subtract that from 14 to find my pH. In fact, I think I'll go ahead and do that now. I'll say pH is equal to 14 minus the POH, right? Now, what we're going to do is go ahead and find the POH. I'm going to get the POH is equal to the negative logarithm of 1.6. All right. So let's go ahead and see what the negative logarithm of 1.6 is. What the heck? Why is all of this stuff happening to me? Oh, come on, man. Oh, goodness. Stuff never happens to me, but yeah, as soon as I get ready to do a recording. Whew, getting upset. Let me not get up. Wait, did I clear this? Okay, 1.6 I'm going to get the log of that. All right. So the logarithm, that's going to be 0.20411998888. But of course, that's only going to be good to 2 significant digits, so that's going to be 0.20. Okay, so I'm going to get the negative of that. Okay, so that's going to be negative 0.20. So POH is going to equal to a negative 0.20, right? All right, now you want to go ahead and report it to the correct number of significant digits because you're going to actually do some subtraction afterwards, okay? All right, so I'm going to say pH is going to equal to 14, and of course this is 14 with an infinite number of zeros behind it, because it's it's infinite number of zeros. So let's go with 3. I'll put 4 right here. Okay, minus, okay, because we're using this equation right here. Now my POH was a negative 0.20. So the negative of a negative is, of course, positive. So my pH is going to equal to 14.20, which is exactly what we got the other way. Now you guys I'm sure you would agree that this way is a little quicker, just a little bit, not that much quicker, but it's a little quicker. So yeah, you'd probably be better off doing it this way, using this equation, pH plus POH is equal to 14. Okay, so going right back to my whiteboard, and I think I just did number 10, right? So number 10 is D. The answer to number 10 is D. Let me check to make sure the answer to number 10 is D. D. Okay, so let's take a look at number 11, shall we? All right. Number 11 says, which of these which solution will have the lowest pH? So now notice that, okay, now the more acidic it is, then the lower the pH. So all I have to do is find the most acidic solution. Since they all have the same concentration, all I have to do is find the strongest acid in here. Okay, now HCN, hydrogen cyanide, is a weak acid. Okay, it's highly deadly, I might add, but it's a weak acid nevertheless. So I can go ahead and disregard. Oh, well, I don't know. Let's see. B, I have a strong acid. It's 0.1 molar nitric acid. I already know what the pH, since it's a strong acid, the acid concentration, the H plus concentration are the same. So my H plus concentration is 0.1. The logarithm of, well, 0.1 is 1 times 10 to the negative 1. So the logarithm of that is negative 1. And the negative of negative 1 is 1. So my pH is 1. All right. So C, sodium chloride, that's table salt. It doesn't have any acidic or basic properties whatsoever, so I can disregard that. The pH of that solution is going to be 7. D, I have another weak acid that I don't have to concern myself with, because I know as of right now my nitric acid solution is going to reign supreme in terms of low pH values. And then E is, I have a weak base. Well, no, that's a strong base. It's a strong base, and the concentration is 0.1. Okay, so I know my answer is going to be B, nitric acid, my 0.1 molar nitric acid solution. So let me go look at number 11 to make sure the answer is B. Yes, it is B. So let's take a look at number 12. Which one of these responses is true with regard to a 0.1 molar solution of a weak acid? Now, I know that a weak acid is not going to completely ionize, so what I know, the fact that I have a weak acid around, that the pH is going to be less than 7, but I know it's going to be greater than 1. How do I know it's going to be greater than 1? Because had that been a strong acid with a 0.1 molar concentration, then the pH would be 1. Since it's a weak acid, it's going to be greater than 1. Okay. A says my H plus constant. Well, let me see. It says which one of these responses is true. Okay. My H plus concentration and my conjugate base concentration. My H plus concentration is greater than my conjugate base concentration. That's not true. Okay. We know they're going to be the same. Well, for the most part. B, the pH is equal to 1. No, that wouldn't be the case unless it were a strong acid, and we know that's not the case. C, my H plus concentration is less than my conjugate base concentration. That's not true. D, my pH is greater than 1. That is true. We know the pH is greater than 1. We know it's less than 7, but we know it's greater than 1. Okay, so the answer is D. Let's see what E is. E says my hydroxide ion concentration is greater than my H plus concentration. That is so not true. Remember, your H plus concentration and your OH minus concentration are inversely proportional. The constant of inverse proportionality is, of course, 1.0 times 10 to the negative 14. So if I took, so of course, once you get your H plus concentration of 0.1, of course, your OH minus concentration is going to be less than that. All right. Okay, so number 13, acid strength decreases in the series. Okay, so we have the hydrogen sulfate anion, which happens to be the conjugate base of sulfuric acid. Yeah, that's how potent of an acid sulfuric acid is. Yeah, it's the conjugate base is it's a weak acid, but it's one of the stronger weak acids around. Yeah, so hydrogen sulfate, then you have HF, then you have HCN. Okay, now remember, the stronger the acid, the weaker its conjugate base. Okay, all right, so which of these species is the weakest base? So of course, all I'm going to do is look for the conjugate base of hydrogen sulfate, which would be sulfate, SO4 2 minus, and that would be B. So that's 13. So let's go down and see if 13, the answer is B. Yay, the answer for 13 is B. All right. All right, so let's see how many more problems I have to do. 1, 2, I'm 3. I have to do 3 more problems. Okay, number 14, which of these species will act as a Lewis acid? Remember, a Lewis acid has an empty orbital. Okay, it has an empty orbital. That's what makes it a Lewis acid. See, remember, Lewis acids accept electrons, and Lewis bases donate electrons. Okay, so Lewis, remember we talked about a coordinate covalent bond or dative bond. All right. All right. The only difference between them and a regular covalent bond is the coordinate. Usually, when you have a covalent bond, each atom supplies 1 electron. So you get orbital overlap in 1 electron. When you talk about a dative bond or a coordinate covalent bond, one atom supplies both electrons in the form of a lone pair, and the other atom has an empty orbital. Okay. So the atom with the empty orbital is the Lewis acid, and the one with the lone pair of electrons is the Lewis base. So all I have to do is find the one with the Lewis acid. We went over this, of course, in class. Boron, of course, in BF4 has an empty p orbital, and it's, of course, the Lewis acid. All right. Number 15, find the pH of a 1.935 molar aqueous solution of melanoic acid. That's something I just pulled out of my behind. Of course, melanoic acid doesn't exist, but I give you a Ka of 2.3 times 10 to the negative 4. Okay, so let's go ahead and find the pH of melanoic acid. Alrighty then. Okay, I'm gonna go ahead and clear my canvas. And let's see what we have here. Now, all right. Now, since melanoic acid is a weak acid, they gave you an initial concentration of a weak acid, and you're trying to find the final concentration. So, of course, we're going to use an ice chart to do this. And I'm going to use my generic acid symbol HA. So I'm going to say HA. And of course, if you want to react it with water, you can. If you just want to ionize it and get H plus cations, you can. I'm just going to go ahead and add the water. Plus H plus yields, let's see, A minus plus H3O plus. Now, then I'm going to put I for initial, C for change, E for equilibrium. Now, initially I have two, let me see, no, I have one, let me change that. There you go. All right, and grab that. So initially I have 1.935. That's my initial acid concentration, and my conjugate base concentration initially is going to be 0, and my H3O plus concentration initially is not 0. Initially it's 1.0 times 10 to the negative 7, but that's so close to 0 that we're going to just go ahead and put 0 there. Okay, now of course if you find Q and compare it to K, I'm going to go ahead and remember it's the same expression, but you use initial concentrations. So of course if I wrote the equilibrium expression for this, I'd have my HA minus concentration times my H3O plus concentration. divided by my HA concentration. Now remember, we don't include water in our equilibrium expression because it's a pure liquid. Okay, the concentration of water is of course going to be proportional to the density of the water, and the density of water doesn't change. There's no point of us putting that in the equilibrium expression if it doesn't change. It's just the number that's just going to get in our way. So we're going to leave that out. Okay, so I'm going to say that's Q. Now if you find Q, you're going to end up with 0 times 0 divided by 1.935. Okay, that of course equals 0. All right, since Q is 0 and K is 2.3 times 10 to the negative 4, we know Q is less than K, or Ka in this case. Since Q is less than K and our initial concentrations have to turn into equilibrium concentrations, the only way that's going to happen if Q is less than K is if I form products at the expense of my reactants. That means I'm going to put a negative X right here. I'm going to put an X right there and an X right there. Now remember, if Q had been greater than K, I would put the negatives on my product side and the positives on my reactant side. If I had a stoichiometric coefficient other than 1 here, let's say I had a 2 right here, I would put 2x right there, okay, irregardless of the value of Q. All right, so it would be either 2x or negative 2x right here if the stoichiometric coefficient right here were 2. But it's 1, so I'm going to put x's right there. So I'm going to say at equilibrium, I'm going to have 1.935 minus x. I'm going to have x, and I'm going to have x. All right. All right, so I'm going to go ahead and write my equilibrium expression. I'm going to say Ka in this case is equal to my conjugate base concentration times my H3O plus concentration divided by my acid concentration. All right. Now, of course, we know the value of Ka is going to be 2.3 times 10 to the negative 4. That's going to equal to my conjugate base concentration is x, and my hydronium ion concentration is also x. So I'm going to put x squared right there, divided by my initial, well, not my initial, my equilibrium acid concentration, which is 1.935 minus x. So, of course, this is, of course, looking like a second-order polynomial. It is a second-order polynomial, okay? But remember the approximation, all right? If 100 times my Ka is less than my initial acid concentration, then I get to take the approximation. So 100 times 2.3 times 10 to the negative 4 is 2.3 times 10 to the negative 2, which is less than 1.935. So that means I get to take the approximation, right? Okay, so I'll just go ahead and write that out. 100 times Ka, if 100 times Ka is less than HA initial, then approximate. Okay. All right. So that of course is indeed the case. So we do get the approximate. So what's the approximation? We're saying that 1.35 is going to be so much bigger than x that 1.935 minus x might as well be 1.935. So we can get rid of the minus x. Okay. So I'm going to say 2.3 times 10 to the negative 4 is equal to x squared divided by 1.935. Okay. All right. All right. So that's the approximation. So, of course, I'm going to multiply 1.935 by both sides to get it out of the denominator and get it on the left side of the equation. 1.935 times 2.3 times 10 to the negative 4 is equal to x squared. Okay, so I'm going to pull up the trusty calculator again that I despise with all my heart and soul. Let's see what I have right here. So I'm going to say 2.3 times 10 to the negative 4 times, let's see, 1.935 is equal to, let's see, a number that's not in scientific notation. That's okay, I forgive them. 1, 2, 3, 4. So that's going to be 4.4. What the heck? Oh, yeah, I forgot. 4.4 505 times 10 to the -4, right? 1, 2, 3, 4. -4. All right. Is equal to x squared. And I'm going to take the square root of both sides to get the value of x. So x is going to be equal to, yeah, that's another thing I get to do. Let's see, where's the square root? Okay, right there. Let's see what happens. Pow. Okay. Now, of course, guys, every time you take the square root or the cubic root or the fourth root of anything, you always report it to one more significant digit. So my answer was already good to 2, so now it's good to 3. Okay. So I'm going to put 0.021. Let me see. 210962. 0962 is equal to x. Now, of course, that's let me see what x is now. Since they asked us to find the pH, didn't they? Okay, x is my hydronium ion concentration, so we're not done quite yet. We still have to get the negative logarithm of this number and report it to the correct number of significant digits. So again, I will say pH is equal to the negative logarithm of my H plus concentration. Okay, so that means pH is equal to the negative logarithm of 0.0210962. And of course, we want to report this to the correct number of significant digits after we get the logarithm of this number, after we get the negative logarithm of this number, of course. So let's see what we have right here, 0.021. Okay, so I'm going to get the logarithm of this number, pow. Get the negative of that number, pow. Okay, so now, of course, I have my answer right here, but we want to make sure we express it to the correct number of significant digits. When we started the calculation, our answer would have been good to 2 significant digits, but we ended up getting a square root. Then, of course, so that means it's going to be good to 3. And then we got the logarithm of it, and so that means my mantissa is good to 3. Since my characteristic has 1 digit in it, that means this answer is good to 4 digits. So it's going to be 1.6758. No, it's going to be 1.676. 1.676. Okay. All right. 1.676. So let's see what that corresponds to. 1.67. Well, 1.68. They only. Well, I didn't make up the. What did I make up this problem? I think I did. Yeah, 1.68. Well, the answer is D anyway. I should have reported it to another significant digit. So, but yeah, the answer to 15 is D. Let me make sure that I have that written down for the answer for 15, D. Yeah, I'm surprised. I usually don't mess up like that. Okay. I guess I need to go back and change that. Okay. I might get around to it. Okay, now number 16, of course, is sodium cyanide. Since hydrogen cyanide is a weak acid, its conjugate base, of course, which is cyanide, is going to be a weak base. And they give you the Kb. All right, so if you guys recall, the weak base problems are going to be very, very similar to the weak acid problems. Of course, you have a different reaction going on there. So, of course, when you solve for X, you find the hydroxide ion concentration, don't you? Okay, so let me go ahead and clear this bad boy out. Okay, all right. Okay, and I'm going to hit paste. All right, so I'm going to say calculate the pH of a 0.021 molar sodium cyanide solution. Okay, so now I'm going to use my generic weak base. I use A minus, and I'm going to react that with H2O. Now, in this case, my H2O is, of course, water is going to act as an acid, so I'm going to end up with HA, a weak acid, plus OH minus. All right. Okay, so of course when I find X of course is going to end up being my OH minus concentration, and we know that we have 2 different ways of getting our pH if we know our OH minus concentration. This time around, I think I'll just use the simple way. I'll just use that equation, pH plus POH is equal to 14. Okay, so I'm going to say I for initials, C for change, and E for equilibrium. let's see, my initial base concentration is 0.021. Of course, I don't care about my water concentration. Initially, my conjugate acid concentration is going to be 0. My hydroxide concentration actually isn't going to be 0. Initially, it's going to be 1.0 times 10 to the negative 7, but that's so close to 0 that I'm going to go ahead and put 0 right there. Of course, now, of course, if we found the K, the Q would be 0, wouldn't it? 0 times 0 is 0, and 0 divided by 0.021 is, well, 0. So Q is again less than my K, my KB in this case. So I'm going to put a negative X right here as opposed to a positive X, which is what I would put had my Q been greater than my K. All right. But since it's less, I'm going to put negative X, and then right here I'm going to put X and X. All right. So at equilibrium, I'm going to have 0.021 minus X. Right here I'm going to have X. Right here I'm going to have X. Okay. So I'm going to go ahead and say that my KB is equal to my HA, which is my conjugate acid concentration, times my OH minus concentration divided by my base concentration, weak base as it is. Okay, I know what the KB is. The KB is 5.0 times 10 to the negative 5. That's equal to well, my conjugate acid concentration, of course, is X, and my hydroxide concentration is X. So again, I'm going to put X squared up here, and my equilibrium base concentration is going to be 0.021 minus X. So again, I'm going to see if I can take the approximation. All right. Now, if you guys recall, the approximation, well, it works for bases, weak bases, the same way it works for weak acids or anything that involves this equilibrium expression. So if I'm multiplying, I'm going to multiply my K, my KB in this case, times 100. If I get something that is less than my initial acid concentration, then I can approximate. Now, as it turns out, I know you guys have these fancy scientific calculators now, so you can solve second order polynomials rather quickly. But let's go ahead and do the approximation way this time. All right, so of course 5.0 times 10 to the negative 5 times 100 is going to be 5.0 times 10 to the negative 3. And 5.0 times 10 to the negative 3 is less than 2.1 times 10 to the negative 2. So I can do the approximation. So I'm going to go ahead and say 5.0 times 10 to the negative 5 is equal to X squared divided by 0.021. So I'm going to say 5.0 times 10 to the negative 5 times 0.021 is equal to X squared. Okay, so let's go ahead and dial up that fancy calculator. Well, I guess it's not all that fancy, but it's okay. It'll do. So we're going to say 5.0 times 10 to the negative 5, okay, times 0.021 is equal to, oh goodness, and this is not in scientific notation. I gotta count. 1, 2, 3, 4, 5, 6. Okay, 1.05 times 10 to the negative 6. 1.05 times 10 to the negative 6 is equal to X squared. So of course, to get X, I'm going to take the square root of both sides. Let's see what we got here. Let me find that square root key. Pow. So that's going to be 1.0249 times 10 to the negative 3. 1.02469 times 10 to the negative 3 is equal to X. Okay, hold your horses now. This is a weak base problem. So we know that X is going to be my hydroxide ion concentration. So I'm going to go ahead and find the POH. Okay, I'm going to say POH is equal to the negative logarithm of 1.02469 times 10 to the negative 3. And get that little decimal point right there. All right, so let's go ahead and get this nice number right here. Get the logarithm of it. Get the negative, say it log. So I get 2.9894. Let me go ahead and report this to the correct number of significant digits. So let's see. I started off, I had two numbers that were both good to two significant digits, apparently, and then I took the square root. So that answer would have been good to 3. Then I took the log, so that my mantissa is good to 3. Since my characteristic has one digit in it, this number is good to 4 significant digits, so it's going to be 2.989 minus POH. So pH is equal to 14.000 minus 2.989. So let's see what pH is equal to. So yes, I'm so glad I'm done and I don't have to use this crappy calculator. All right, let's see, 14. Well, I shouldn't say that. It's not that crappy. It's minus. I'm just fond of my own calculator. 989. So 14 minus 2.989. That's 11.011. I wouldn't be surprised if I have 11.01 up there, but yeah, but you guys get the idea. 11.011. So let's see what we got here. Oh yeah, I do have it up there. 11.011. It looks like I didn't have it and I changed it at some point. So the answer, number 16, is E. So let me make sure 16 is E. Okay, so that would be the end of Chapter 16 study guide. All right, so hopefully you guys will do great on the exam. All right, so yeah. All right. So I'm going to call it quits. Peace out. Okay, guys.